All right, good morning.
Morning.
Well, welcome to Friday. Um, this is the end of week 9. And as a reminder, next week we only meet 2 days, Monday and Tuesday. Wednesday through Friday are holidays for students. And then we come back the following week for one more week of classes, and that's it. We're done with the quarter. So after today, we've got basically 7 meetings left, which is not a lot, but we've done a lot of we've made a lot of progress in this course, and we're in good shape material wise. So any questions before we jump back into stuff?
Is there a way to time certain processes in your program, not just the whole program? Because I'm sitting at like 19 minutes to process test 4.
Hmm.
And I
Um.
know it takes a long time, but that seems like an excessive amount of time.
Yeah. So I mean, you could put some checkpoints into your code, and do things like you know, print out a timestamp throughout your code. So like maybe each time that you get a new phrase, or every 1,000 phrases that you collect or something, throw a marker out, something like that.
Oh, I guess I could do that, huh? Put it in the for loop and then just have it
Yeah,
put
yeah.
a timestamp at each spot.
Mm-hmm.
Okay.
If you run this on the server, it should not take that long. Um, it should
Yeah,
take.
that's on the server.
Okay. Interesting.
I haven't tried to pull it to my local yet, but I mean, I have terrible internet, but I don't think that would change anything.
No, that shouldn't affect the running speed because there's not a lot of I/O going on. Um,
Yeah.
it's interesting. Let's see.
And I mean, the output is perfect, so the program works. I'm just wondering if there's a faster way to do certain processes or something, because everything to clean up everything is tr and sed.
Right. Um, so yeah, so there's some contention going on for the CPU. So there are look like some stray jobs that maybe I need to like kill, um, because let's see, well they're in the different section, but there's someone who's got a number of instances running, some of which have a few hundred minutes of CPU time. So those are probably runaways. And you've got a few jobs running with a few hundred minutes of CPU time also. So if you execute the
Oh,
command,
so
go
I stayed logged in last night on accident, but
okay, yeah, if you run the command top, you'll see which processes are taking the most CPU time. Um, and so there's a few that might be runaway processes.
oh, gotcha. Okay. Yeah, yeah. I stayed logged in last night, but
Okay, cool. The
I was
CPU is
just
okay though. The CPU is, well, actually our load average is really high. Um, yeah, so I might do some maintenance and kill some runaway processes later. Um, but yeah, if it works eventually, that's good. The only real sort of possible concern with taking a long time is if you're not using the associative array like an associative array. For example, if you're looping through the array each time you get a phrase and explicitly looking for that phrase to tally it, then that's going to take a really long time. And that's not the strategy you want to use. But other than that, it's probably okay.
oh,
Uh, For test 4, the regex creating the array only took 6 seconds. Echoing each value one at a time took 10 minutes. That's unusual. You should be able, I mean, it should be really fast once you've finished parsing all the input to just loop through that array and print out each value. That should be more or less instantaneous. There should be no noticeable delay there. So that's a little surprising. If yeah, don't know of n when you can know of one, exactly. If your code is on GitLab, you're welcome at this point to send me an email and say this is taking a really long time. Am I missing something major? And I can take a look at it. I won't do that next week because that'll end up being all I do. But if you want to do that today, feel free. And
yeah, I'll send you one right now.
Okay, cool.
Cool, thanks.
Yeah. And yeah, this is getting into this notion of order of complexity, which is something we'll talk about a lot in CSE222. But there's this notion of how fast is my computer, and that's kind of a silly notion in some ways because fast is relative, right? So today's computers are faster than computers from 80 years ago. There's not a lot of debate about that. But you go to the store and you start looking at the little 3x5 cards below each computer with the specs on it, and it's Intel Core, blah blah blah, dual this, quad that, and X number of gigahertz, and what does that mean, right? And if you take Engineering 270, the PIC processor runs at 31 kilohertz, and what does that mean, right? So just measuring kind of bare speed of processors is a tricky business. And to say how long will my program run, how efficient is this algorithm? Well, it depends what you're running it on. If you run this PA5 on a PIC processor, it's going to take an eternity. If you run it on a cutting edge gaming laptop, right, it's going to run a lot quicker. If you run it on the Linux server, that's a virtual box that's single core, and that's going to be fairly clunky. And so what is meaningful though when you're looking at algorithms is how efficient are they in terms of the size of the problem. And so, for example, when we think about sorting, if you, and this is again, it's like a 222 topic, but it's kind of topical right now. If you think about sorting a set of numbers, right? So here's a bunch of numbers you want to sort. How do we do this by hand? Well, maybe, I go through here and I look for the biggest number and I move that to the bottom. And then I go through and I look for the biggest number after that and I move that to the bottom. And I keep going through looking for the biggest number and putting those up here until I've sorted all my numbers. And if I have 100 numbers, I have to do basically 100 things to find the biggest number here. I have to look at each number and compare it to what the largest number is I've seen so far. So that's 100 operations. And at the end of those 100 operations, guess what? I found the biggest number. Well, now I have 99 numbers left to sort. I have to do 99 operations to find the biggest number of these and put that here. And then I have to do 98 operations to find the biggest of these and put that there. And so I'm going to end up doing this number of operations. All right, how long does that take? Depends on the program. Depends on what language I wrote it in. Depends on what type of silicon the CPU was built on. Depends how many other people are using the machine. But here's what's interesting. If I think about how long it takes, particular machine, particular architecture, particular language, and so on. If I think about how long it takes to do 100 problems, 100 numbers, and then I think about how long it takes to do 200 numbers, I'm going to find that this is 4 times whatever that was. And so by doubling the amount of data, I'm quadrupling the amount of time I need. And that's an interesting ratio to analyze. And the notion is that when I increase my amount of data by n, I'll increase the time it takes by n squared. And that's what we call an order n squared algorithm. And a lot of sorts, a lot of searches end up being order n squared. And if we didn't use an associative array and we wrote PA5 just by taking a phrase, searching through our list of phrases to find where that phrase is, or to note that it's a new phrase and then added it, right? That would be an order n squared. And so if sorting something with 10 phrases took, 1 second, sorting something with 100 phrases would take 100 times as long, right? Well, sorting 20 phrases would take 4 times as long. Sorting something with 10 times as many phrases would take 100 times as long. And sorting something with 1,000 phrases, so this is 100 times larger, would take 10,000 times as long, which is about 3 hours. And so order n squared is a brutal kind of algorithm. Now if we use associative arrays, this comes down to order n. An associative array doesn't go through and look at each element to figure out where your phrase is and how many times you've seen it. So if I can do 10 things in 1 second, I could do 20 things in 2 seconds, 100 things in 10 seconds, 1,000 things in 100 seconds. It's under 2 minutes versus 3 hours. So if you're using an associative array well in PA5, we shouldn't see the times really blowing up. They should be growing linearly, as opposed to if we're not using an associative array, they're going to grow as n squared. Someone said, is it possible to O1 PA5? Not on a conventional computer, because we have to, I think it's going to be at least order n, because you have to ingest the data and store it. But it's possible to make the process of breaking up a line of input, cleansing it, breaking it into phrases, storing each of those, tallying those. You could get that down to order 1. But then if you have n lines of input, you still got to do n operations. But I think there's probably ways on unconventional computers that we could do this in order 1. For example, you and I could look at a piece of paper with 5 things written on it and probably recite to somebody, how many times each phrase occurred without going through a sequential algorithm. We have some way to sort of process that image data in parallel and tally it, tally the different phrases simultaneously, perhaps. But definitely an unconventional computing type of architecture. All right, so that was a bunch of stuff that I didn't bother tagging, but a bunch of miscellaneous topics there. Peripherally related to execution speed for PA5. So let me make a few comments on reading input in Bash, and this idea of once we've got our code written for PA5 so that we can take a single line of input, clean it, break it into phrases, tally those phrases, then you've got to do the whole thing inside a loop so that you can repeatedly read input until you hit the end of the input, and then do whatever you want to do. So let me write some code here. So let me write a loop one. So I want to write a loop that that reads one line at a time from the user, and then continues until the person hits Control D to exit out of the loop. And we talked about how we could do this by using the status variable $? To see whether the read succeeds or fails. Here's a different way we can do this. So we can say while read, whatever our line variable is. All right, so what's going on here? We're just going to prompt the user once and say some stuff, and we've got a while loop here, but this is a different kind of while. We're saying while read and the name of a variable. And so what this will do is basically wait for the user to type something and hit enter. And whatever they type, that will go into this variable line var, and we'll execute the body of the while loop, which in this case is just one line. We'll say you said and show them the line var value. And then we'll go back up here and read another line. And each time we come to the top of this while loop, we'll read a line of input from the user, and then we'll execute the statements in between do and done with this variable equal to whatever the person typed. And this will continue over and over until the person hits Control D. And at that point, this while loop will exit and will come down and execute the statements after done, which in this case is just a goodbye message. So if I run this, Alright, so if I run this is a test. Hello, cool. If I hold down Control and hit D, then it tells me I'm done with my input, and it says goodbye. Alright. Yeah, we took attendance in the beginning, so go ahead and send me a ping. Maybe we didn't do attendance in the beginning. All right, so this is one way to read standard in a loop. Do things to each line of input that you read, and then exit when you hit end of file. So all the stuff that you may have developed for reading a single line, cleaning it, breaking it into phrases, tallying those phrases, that can go inside the body of a while loop like this.
So the if statement you were talking about yesterday, if $, question mark is not equal to 0, so you don't need to do that with the while loop?
You don't need to do that with the while loop. You can do that. So what we did yesterday was we did something like while 1 equals 1.
Oh,
Do so something like that. So read a line variable, and then we just checked the status value, and if it was non-zero, that meant they hit end of line, um, and we break out of our loop. Otherwise, we go back up, and this is just set up as a forever loop. So this will do exactly the same thing. But this is a little easier to write. So a while read. Now, we're reading from standard in, we're signifying end of input by hitting a control D. But if we run one of these and we redirect our standard in from a file, so test file, then instead of reading from the keyboard and waiting for control D, it reads each line from the file. And when there's nothing left in the file, that triggers the end of file indication, and that while read line statement will exit and will come out of the loop. We also have the option, if we want to process one file in particular, on our done statement we can say less than and the name of a file, and now instead of reading from standard in, this script will read automatically from this file. And so it works exactly the same as the previous version, except instead of reading from standard in, it reads from this. We're basically redirecting our input inside here, but we're not redirecting all of standard in. We can still say something like right, we can ask them who they are and read a name, and and then we can say some stuff. So who are you? I'm Nick, and it'll say hello Nick, and then it goes ahead and it reads from the test file. So we're just saying read from this file instead of reading from standard in up here. And with any of these, we can also execute a command and send the output of that command to standard in of our loop program. So L1, takes whatever we type and we echo. We can redirect from a command like this. We could also say, let's do PS, let's see what processes are out there. I could say PS and pipe that into L1. And now it's running the PS command, taking the output of that and running L1, but instead of reading from standard in, it's reading from the output of this command. And so my program is seeing the output of running that process status command, and it's showing me the stuff that P1 would show me. Or if I run the calendar, I can see, current calendar line by line. And this one's a little goofy, but we can also do this inside a file. If I wanted to execute a command, I can do 3 less than signs, a back quote, and whatever command I want, ls. And this will execute this command, capture the output, and use that line by line each time that I come back to the top of my while loop and I try to read into this line variable. So as I run this loop, it's going to basically set line variable equal to each line of output generated by the ls command. And so now I could have, a bash script that's doing something like looking at the files in my current directory by virtue of the ls command. So there's a variety of options. The most topical for PA5 is probably just this one, or the one we went over the other day where we just check the status variable. But either of those are good to use. All right. Let's go back to regular expressions. fix this. So I found a typo in here, previous class. So this is on Canvas in the top area of basic information. There's two entries in here: regex summary and regex practice questions. And other than a small typo here, where the formatting got eaten. All right. So this is a short synopsis of what we did yesterday with regular expressions. So this idea of anchors to match something at the beginning or the end of your input line. Period is a wildcard to match any character. An asterisk matches 0 or more instances of the previous character, whatever you put right before the asterisk. If you put a pattern inside parentheses, then whatever matches that pattern gets saved in what we call the register. Registers are numbers starting with 1 for the first one and so on. And when we say backslash number, we're asking for the contents of a register that was loaded when we matched a pattern. Most characters just match that character explicitly unless the character is special. For example, a period, a $, a caret, and so on and so forth. If we want to match a special character, we put a backslash in front. So if we're looking for a $sign in your input, we can say backslash $sign, that'll match a $sign. If we don't put the backslash, $sign means the end of the input, right? The anchor at the end of the line. And we can match multiple characters by putting them inside brackets. We can match everything except a set of characters by putting them in brackets with a caret in front. And that was pretty much the full set of regular expressions that we went through yesterday. Again, you know, tiny little piece of the subject. There's a whole lot more you can do with regular expressions, but this is a pretty rich subset that lets you do a lot of different processing on strings. And I think it's better for me, when I'm learning a topic, I don't want to learn, 100 different things. I want to learn 5 things and get really good with them. And so here's, fewer than a dozen concepts related to regular expressions that if you get really good with them, you can do all kinds of stuff, all kinds of manipulations and modifications on strings. Is it possible to use anchors with TR? So TR is really just a straight translation, but I'm not sure what an anchor would mean there. Because TR, so the short answer is no. TR basically takes every piece of your input and applies a translation to it to generate an output. But we can combine TR with sed, for example, and if we wanted to do something in some case at the beginning, we could, throw a special marker in the beginning and then use TR to translate that maybe. And so these expressions work. We've been playing with them with sed, so we can say sed. And this reads from standard in, applies this pattern change, writes the output to standard out. And so that's what this is referring to here. And this replaces the first occurrence of this pattern with a new. If you put the /g at the end, it replaces every occurrence of the old with a new. And in sed, we do it with sed quote, and we put the command in there. We can also do this in VI. And so there's a variety of things available here. So we can say colon substitute bin/bin. And so on the line that I was currently on, it made that substitution. I can change each lowercase b to an uppercase b by putting a g at the end. And get like that. I can also apply these expressions to a range of lines. So I could say, you know, here's line 2. So let's go between lines 2 and 4. And let's change the first occurrence of E to 3 uppercase E's. Let's do that for 2 through 5. There we go. And I can do something on the entire file by saying :1, comma, and then if I don't know what the number of the last line is, I can just say $, and that means the last line of the file. And I can say, let's change all my E's to uppercase E's like that. And you can use, you know, basically line 1, comma, line 2 to replace on every line. Between those two inclusive, $ means the end of the file, period means your current line, and you can do arithmetic. So if I know that I want to change, you know, stuff in this while loop, I can say : dot -3, comma, dot. Well, dot means the line that I'm on. This is dot -1, -2, -3 would be my while statement. So everything on these 4 lines will get changed. So dot -3, comma, dot, substitute E with big E's globally. And so I've made a change on those 4 lines. Or sometimes, you know, I'll come here, hit a Control G and see, oh, this is line 5. And then I'll go to where I want to apply my change through, and I can say 5, comma, dot. And put in my substitution pattern. Now, how often are you going to do this in a 5-hour coding session? You know, maybe once every few days. So this is not something you try to memorize, right? But it's something you note. It's something that, you know, somewhere in the back of your mind you remember there's a way to use regular expressions to make changes on multiple lines in a file in VI. And, you know, someday you'll be writing some code and you'll have a function that's 27 lines long, and you'll realize that everywhere in this function, you know, I used the variable blah and I really meant the variable blah-de-blah, right? And it would be nice if you could just sort of, with one command in VI, change all the occurrences of blah to blah-de-blah in between those 2 lines of your file, right? You can do it with one statement. You can do it with one command starting with a colon. And so, you know, that happens, you know, remember, hey, you know, somewhere way back in 2021 I learned how to do this. Go and do some Googling or dig up your notes or something. And if it works for you and it's slick and it saves you some time, you'll remember it, right? Or you'll remember more quickly that this is an option. The next time you have to do it, you'll get there more quickly and so on. So that's the spirit of like all of this VI stuff. Let's see. Using sed for that is when it's possible to make tr only translate something at the beginning of a line. Interesting. So if I wanted to use tr to say uppercase the first word of, yeah, there's probably a way to do that, I'm guessing, actually. I think tr is probably way more powerful than, but you know, if I wanted to only uppercase the first word, I might tie it into awk or something, which we haven't talked about yet. Yeah, tr won't handle it itself, but yeah, doing it with sed's probably a good way to go. All right, so there's a less than 1-page synopsis of regular expressions as we've discussed them. And so the other thing that I've posted here is regular expression practice problems. And I'm not going to ask you to turn these in. I'm not going to grade them and so on and so forth. But you might see some regular expression question on the final exam. And so I do want people to come out of this course, you know, understanding regular expressions and being able to write at least some basic regular expressions. And so here's some problems you can practice on. And if you want to play around with these a little over the weekend, we can talk about these in class on Monday. But let's go through a few of these right now, and just sort of think about them. So we worked through some of these in the earlier section. You can listen to the lecture on that. Let's look at some of these. How would you remove the last character from a line? And if you want to send me a direct message in chat with a said statement for this, we can do that instead of just shouting it out to the class. But let's think about this. How would you write a said statement to remove the last character from a line? Cool. Awesome. Looks good. All right, so I think people are getting this. So yeah, basically we hello. Basically, right, anytime we're trying to use a regular expression to do something like this, the first trick is how do we recognize the thing that we're interested in, you know, potentially changing or removing and so on. We don't know what the last character is, but we know that it's at the end of a line. So a pattern to find the last character might be a period followed by a dollar sign. And if we just say substitute dot star slash slash, right? This will match, the period matches everything in your input line. So a period matches this, but it's not followed by the end of the string. A period matches the E, but it's not followed by the end of the string. The only way that we can do this is if the period matches this E, and that is followed by the end of the string. So this pattern matches the E, and then we say replace that with nothing. That gets rid of that last character. Right, so that gets rid of the last character on a line. So what if you want to remove the last three characters from a line? Yep, exactly the same idea. So if you look for dot 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 dollar sign, that will only match when these three dots correspond to the last three characters followed by the end of the string. So that would get rid of the last three characters. And if we did this, that would get rid of the first three characters. And in fact, the anchor is optional here because set always starts at the beginning of a string. So if I do something like this, and I do A, B, C, D, E, F, G, it gets rid of the A, B, C. But even without the anchor, since it starts at the beginning, the first three characters are going to match that dot, 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 and so the A, B, C gets taken out. All right, so one thing with regular expressions is sometimes it seems relatively easy to do one thing, and then to do something slightly different is a whole lot more complex. And so what if we wanted to remove the first three and the last three characters from a line with a single sed statement? And we can do this with two statements, right? We could say, let's take what's at the beginning of the line, remove the first three characters, and then pipe that into sed. And remove the last three characters. So if I do A, B, C, D, E, F, G, that just gets rid of everything in the beginning and the end and leaves me with a D. But what if we wanted to do this in a single statement? And this is going to require registers.
Can you say that again? We're looking for which character?
Remove the first three and the last three characters from a line.
Okay. In one command?
Mm-hmm. Cool. All right, good answer. Excellent answer. And the trick here is, you know, we can match the first three characters like that. We can match the last three characters like this. But unless our statement happens to have 6 characters in it, just doing this pattern is not going to match. There's going to be some stuff in between the first 3 characters and the last 3 characters. And we can match that stuff with a dot star. And so this will match, you know, our entire line. But this part of the pattern will match the first 3 characters we want to get rid of. This will match the middle characters we want to keep. This will match the end characters we also want to get rid of. And so if we throw this part in parentheses, we could just replace that whole pattern with \1, which is the middle section.
So what if the line contains only 5 characters?
Then the pattern match will fail, and it will not change the line at all. But let's see if that's actually correct. So I'm going to go beginning of the line, 3 characters that I don't care about. Any succession of characters, and I do care about those, so I'll put them in a register. 3 final characters followed by the end of the string, and let's replace that with whatever we matched in that middle section. So that takes off alright, so that's doing the right thing, but if we don't have enough characters, the whole pattern match will fail. And so it doesn't do any substitutions. When we did this, where we used a pair of sed commands, if I don't have 6 characters, well, that first sed command is still going to succeed. So it's going to remove the A, B, C, but then the second sed command will not find 3 characters, and so this should just leave me with D, E. and depending on what you want to do with edge cases, you know, you might do one or the other. Is performance faster when doing it in one command? Good question. I really don't know. For one thing, if you have multiple cores on your machine, you might be able to do, you know, 16 commands and have them execute in parallel, and that could be faster than a big complex set statement. So I don't know. I could see it being faster or slower. So so I'm going to invite you to play around with these and see what you can do with them. And you know, they're increasingly difficult. So the basic patterns are basically just using wildcards, or maybe a wildcard with an asterisk, and then using carets and dollar signs to do things specifically at one end or the other of your input. And then the more complex questions are the ones involving registers, where you're capturing part of your pattern and doing things with the captured parts, and then playing around with brackets to do ranges of characters and so on. And as I mentioned, there's some cool websites available that'll let you play with regular expressions, and they're so cool. I don't seem to have bookmarked any of them. So let's put a test string down here. This is a test. And so I can search for, you know, I, and it will tell me it found two matches for I right here and here, right? If I say space, parentheses, period. Oh, so on a lot of these web tools, they don't want you to escape your parentheses. So now I've put in a regular expression, which is a space followed by any character, and so it's matching these highlighted sections, right? So space I, space A, space T, and over here I can see each pattern that matched, and they're calling them groups instead of registers. But register 1 contains the letter I, that was the thing after the first space. Register 2 contains the letter A because I matched space A. Register 3 will contain the letter T because I matched a space followed by a T. And so you can build up a regular expression in here and sort of see interactively how it's being applied to a particular input string. And you can see explanations of it up here as to what's going on and so on and so forth. So, and that's just kind of a random site I Googled, but I'll bookmark that. So, so that's pretty much regular expressions. The backslash is an escape. So, when we do this in sed or vi, if we have a parentheses, it's just looking for a parentheses. So we put a backslash to say, hey, I'm not looking for a parentheses, I actually want to take this pattern and take what matches and put it into a register. And so we're telling it to treat the parentheses as a grouping indicator. All right, so that's all I'm going to do with regular expressions. But we will talk more about sed next week or the week after, and actually look at how we do sort of small programs in sed. Oh, the backslash on that side. So when you do a backslash on the right hand side, that means the contents of, in this case, register 1. So the parentheses over here said take whatever matches this pattern, save that in register 1. This says use the contents of register 1 as the thing you want to replace with. So it's reading out the value of that group or register. All right, we're out of time. Send me an attendance ping on the way out, please. And have a good one, and I will see you all next time.